Hi everybody, in this video I am going to go over a multiple choice test based on the topic of gases. So let's get right to the first question. Number 1. Find the density of dinitrogen tetroxide at STP, or standard temperature and pressure. So for this question, we have to find the density, which is grams per liter. Now let me write that more clearly, grams per liter. And we have to know a few things. At STP, you can either memorize that it's at 0 degrees Celsius and 1 atm, or you could memorize that 22.4 liters are in 1 mole of gas at STP. Knowing this, we know that the number of liters in 1 mole is 22.4. So if we find the number of grams in a mole of dinitrogen tetroxide, then we will be able to divide grams per liter and thus find our answer, which is our density. So let's try that. Dinitrogen tetroxide is N2O4. So knowing this, let's find the molar mass of this. N has a molar mass of 14.01, and you'll just multiply that by 2, and you'll add that to 4 times 16.00. And on my calculator, I will solve for that, and 2 times 14.01 plus 4 times 16, and we get an answer of 92.02 grams per mole for the molar mass of dinitrogen tetroxide. Now, in 1 mole of dinitrogen tetroxide, there are 92.02 grams and 22.4 liters. Notice how this can be written as a ratio. So we can say for every 92.02 grams of dinitrogen tetroxide, there is 22.4 liters. Since this is the amounts in 1 mole of the dinitrogen tetroxide. So all we have to do is simplify this ratio in order to find the density in grams per 1 liter. So dividing the numbers, 92.02 divided by 22.4 is actually going to be 4.10 grams per liter. And that's our answer, D. Notice how there are many ways to do this question, and the way I did it is just a quicker way for me to solve the question, knowing the amount of grams and the amount of liters per mole, and by dividing the two, I got the density. So that's just a neat trick, and let's move on. At low temperatures, the Maxwell-Boltzmann distribution for radon is blank and blank, while at high temperatures, it is blank and blank. So let's try to figure out what this means. A Maxwell-Boltzmann distribution tells you the distribution of, the molecules at different speeds. So I'll write F as the frequency at which it happens. So at low temperatures, remember that the variety of speeds is low, since at low temperatures you can only attain as much speed as you can, and it's not that much. So therefore the range is low, and thus the peak is very high, since the molecules are restricted to these speeds, and thus they have a high frequency of occurring at these speeds. Now at high temperatures, the curve is much wider, since at higher temperatures you can attain a higher maximum speed, since temperature is related to the kinetic energy, which is related to how fast molecules move. So the peak will be lower because the molecules can spread out over many different velocities, and thus the frequency of each velocity is low, since, they can have many different speeds, and the speeds are all spread out kind of evenly. And let's answer the question now. At low temperatures, the distribution is, it's to the left. Well, let me do that in blue. To the left, and it is a high peak, so it's a tall peak. And for the high temperature, which is written in red, it's to the right, and it has a wide peak. and it looks like B will be our answer. Number 3, 2.00 liters of oxygen gas and hydrogen gas react completely with each other in a closed container under fire to form 0.500 grams of water. What is the partial pressure of oxygen gas before the reaction if the container before the reaction was at 25.0 degrees Celsius? And let's try to figure this out. Well, let's write the reaction between O2 and H2 first. O2 plus H2 becomes H2O. We're going to put 2 there and a 2 here, and our reaction is balanced. So, in order to find the amount of gas before the reaction, we have to kind of think backwards. This H2O used to be these two things, and it says that the oxygen and hydrogen reacted completely to form that. So as a result, we can go backwards and see how much of each we needed to form this. So it says we formed 0.500 grams of water. Now we just have to find the moles of water because we read reactions in moles. So divide 0.5 by the molar mass of water, which is 18.02, and you get, well, let's see. You get 0.0277 moles of water. And I'm not going to keep extra digits since our answer will be very close to the actual answer in the multiple choice. And thus, I don't have to be that accurate since if it's close enough, I could just pick it. So if 0.0227 moles of H2O formed here, then according to the reaction, the same number of moles of H2 formed, so 0.0277 moles of H2 were used, and for every 2 moles of H2O that we produced, we used half as many moles of O2, so we have to half this number, so 0.0227 divided by 2 is, well, 0.0139 moles of O2. Now that we have the moles of O2 and H2 that reacted with each other, and note that they reacted with each other completely since it's a 1:2 ratio, and thus let's find the pressure of the oxygen gas before the reaction. So in order to find the partial pressure, we can do a few things, but this is what I'm going to do. I'm going to find the mole fraction of O2, and I'm going to multiply the mole fraction by the total pressure to get the partial pressure, since that makes sense to me. So to find the total pressure, we simply have to do PV equals nRT. So the pressure, well, I don't know what the pressure is, and the volume, 2.00, is equal to N. And remember, at the total pressure, we are counting all the moles. So in the beginning, we had this many moles of gas. So you have to add up 0.0139 plus 0.0277, and I get that we had 0.0416 moles of gas at the beginning, and this includes both O2 and H2, and we had to multiply by 0.0821, and then we had to multiply by the temperature, which is 25 plus 273.15, which is 298.2. So now that we have this, let's just solve for P. 0.0416 times 0.0821 times 298.2 and divided by 2. And we get that the total pressure is 0.509 atms. But we want the partial pressure of O2, so we have to multiply by the mole fraction for O2. Now the mole fraction for O2 is just the moles of O2, so 0.0139 over the total moles of gas, which is 0.0416, and I get a mole fraction of, well, let me figure it out, 0.0139 divided by 0.0416, and I get 0.334 as my mole fraction for O2. Now simply multiply mole fraction by the total pressure to get the partial pressure. So 0.509 times 0.334, and we get that the partial pressure of oxygen gas is 0.170, and that's our answer. Next question. Vapor pressure is defined as the pressure exerted by the gas formed from the vaporization of a liquid. B, since vapor pressure is the pressure caused by the gas particles that evaporated from the liquid. Number 5, a student wants to use the ideal gas law for his calculations for a sample of helium gas in a sealed container. What should the student do to make his data as close to the true value as possible? So in other words, the student wants to make the gas as ideal as possible so that the student does not have to use the real gas law in order to make up for the deviations due to the attractions or the size of the particles. So he has to make sure that his gas is ideal in order to use the ideal gas law. I mean, that's why it's called the ideal gas law, right? So he has to make it so that his experiment is not at a high pressure and not at a low temperature. Remember, these are the conditions that make the gas deviate from the ideal gas. So we have to make sure that these two don't happen. So do the experiment in the freezer. Oh, that decreases his temperature, makes the gas less ideal, and that will ruin his data. So A is out of the picture. B, increase the pressure to 1,000 atmospheres worth of pressure. Now, that's wrong too, because increasing pressure makes your thing closer to the liquid state, and that's not what you want to do. C is in the same boat. Pumping helium into the container only increases the amount of helium that you have, and that increases the pressure, since remember, moles and pressure are directly proportional if you derive it from PV equals nRT. So C is out of the picture since adding helium increases the pressure, and pressure increases cause the particles to be closer, and that makes them closer to the liquid state, and that's not good. D, do the experiment in a hot bath. Well, yeah, that's correct, because by doing the experiment in a hot bath, you are increasing the temperature and making the gas more like a gas and less like a liquid, since it's the opposite of this, and that's what we want. So D is the answer. Number 6, a student adds 0.0500 grams of water to a sealed 100 milliliter test tube filled with only neon gas. Assume that the volume of water is negligible. So let's draw ourselves a picture. This is 100 milliliters. You have a little bit of water down here. Let me do that in blue, actually. And it says the volume of the liquid is negligible, so we can assume that the volume of the gas is 100 milliliters, since if the volume of the water is so small compared to the volume of the container, that means that we can think of it as if the volume of the water didn't exist in the first place, since it's so small. And because of that, you can assume that the volume of the gas is equal to the volume of the container. Now let's read on. At 24 degrees Celsius, the water vapor pressure is 22.4 millimeters of mercury. Once the system reaches a water vapor pressure of 22.4 millimeters of mercury, the student opens the test tube, pours out the remaining water, and weighs the water. How much will the scale weigh? Well, for this question, you have to think about what water vapor pressure is and how it works. So in our test tube, I'll erase this. We will have a test tube filled with neon gas, which we won't show. And note that when you seal it, the only gas that's in it is neon gas, and there's no H2O gas. And remember that when you have a liquid, the liquid wants to have a liquid gas equilibrium and wants to have a water vapor pressure at 22.4 millimeters of mercury at 24 degrees Celsius in order to reach equilibrium. So the container wants to have a water vapor pressure of 22.4 millimeters of mercury. But at first, you only have neon gas, so you have to make this pressure. And how do you make it? Well, the water can simply just evaporate to form that pressure, and that's what it will do because it wants to reach this water vapor pressure. So let's figure out how much water evaporates in order to create this pressure, and see how much water is left over, which is essentially what the question is asking. So let's find out how much water vapor is needed in the air in order to make it 22.4 mmHg. So 22.4 millimeters of mercury is 22.4 divided by 760. It's a pressure of 0.0295 atms. And let's just use PV equals nRT to find the number of moles of water it takes to create this pressure. So our volume is 100 milliliters, or 0.100 liters. And this is equal to the moles of water times 0.0821, and times its temperature, which is 24 plus 273.15, and that's 297. And doing the math, you get 0.0295 times 0.1 divided by 0.0821 divided by 297, and you get that the number of moles of water needed to create this water vapor pressure in the container is 0.0001298. And let me just underline the third sig fig because we have to keep track of sig figs. And this is the moles of water, but we want the grams of water. So we multiply the moles of water by the molar mass to get the grams of water. So multiply this by 18.02, and we get that a total of 0.00218 grams of water evaporated. So if this much water evaporated to create the water vapor pressure that we wanted, then how much is left over? Well, if you have originally this much and you subtract this, you will get the leftover. So 0.0500 minus 0.00218, and we get that we have 0.0478 grams left over, and that's C. Now let's move on to our next question. So let me clear the ink and say that this is C. Find the ratio between the fusion rates of H2 gas, hydrogen gas, and sulfur hexafluoride gas. So notice how I'm not giving you the formulas. I'm making you read the formulas and deriving them. So sulfur hexafluoride is SF6. Now, the fusion rates between these two, we're assuming it's at a constant temperature because it doesn't talk about anything related to temperature, so we can just assume that. And we just have to find the molar masses of these two. This is 2.02, and sulfur hexafluoride is, let me check my periodic table, 32.07, and fluorine is 19.00. So you do 32.07 plus 19.00 times 6, and you get that the molar mass of sulfur hexafluoride is 146.07 grams per mole. Now to find the fusion rate, it's simply R1 over R2, and we'll call hydrogen gas R1 and sulfur hexafluoride R2, and this is equal to the molar mass of SF6, which is the second one, so 146.07 over 2.02, and this is all square rooted, and when you do the math, you take the square root of 146.07, you divide it by 2.02, and you get that R1 over R2 is equal to 8.504, and this is closest to D, and notice how it says 8.50321. Now that's the same thing as 8.503, since 8.503 over 1 is still 8.503. They mean the same thing. So let's go on to the next question. Which gas at 600 Kelvin has the same diffusion rate as methane at 150 Kelvin? Now for this question, it's a little bit hard because it comes from the Chemistry Olympiad, but that's perfectly fine. If you watch the videos about how I derived Graham's law and the other law relating temperature and diffusion rate, you will know that I used K equals 1/2 mv squared. So let's read this problem and see which one of these three are constant. So it looks like our temperatures are not constant. It looks like our gases are not constant, which means that the masses are different. But it looks like the effusion rates are the same. and this is velocity. So velocity will be constant in this case. So let's derive an equation for this. So remember that K is temperature, M is molar mass, and V is either V or the diffusion rate, R. So it says the diffusion rate is a constant, so we have to keep the constants on one side and move everything else to the other side. So I derived the equation by moving the M to the left side and moving the 1/2 to the left side by multiplying both sides by 2 to get this. Then I labeled each one as T1 and T2. In order to set up two different situations, I combined them over here, and last but not least, I simplified them and I got this relationship. T1 over MM1 is equal to T2 over MM2. So now that we have this equation, we can start solving. So our T1, let's just say that this will be our first scenario, and this will be our second scenario, and let's just solve it. So our T1 will be 600 Kelvin over the first molar mass, which is unknown, and it's equal to T2, which is 150 Kelvin, and the molar mass of the second thing that we're looking at is methane, and that's 12.01 plus 1.01 times 4. It's around 16.05, I'd say. And doing the math, you have to plug this onto your calculator and solve for MM1. So let's see what happens if I solve for this. I get a molar mass of 64.2 as the molar mass that we need for the substance. So this substance or gas has to have this molar mass. So not helium, not oxygen. Now sulfur dioxide has a molar mass of 32.07 plus 2 times 16.00. And doing the math, you get, you get 64, and 64 is really close to 64.2. So C is our answer. So for this question, you noticed how it's nothing that I've ever talked about, but it's something that you could have figured out by looking at the fundamental relationship between temperature, diffusion rate, and mass using K equals 1/2 mv squared. So let's take a look at the next question. A vessel contains 66 grams of carbon dioxide and 16 grams of oxygen gas at the pressure of 10 atms. What is the partial pressure of CO2? Well, notice how we have the total pressure, and we can find the partial pressure of CO2 by finding the mole fraction for CO2. Now we have to convert everything from grams to moles. CO2 has a molar mass of, 44.01, and oxygen gas has a molar mass of 32.00. And doing the math, we can divide 66 by 44.01. We get 1.5 moles of CO2 about, and I think 0.5 moles of O2. And adding that all up, we have a total of 2 moles of gas. So the mole fraction for CO2 would be 1.5 over 2, and that will give us 0.75. If you multiply 0.75 by 10.0, you will get 7.5 atms, and that is our answer. Let's move on to the next question. Question 10. In the diagram above, the paired open spheres represent H2 and the paired solid spheres represent N2. When the molecules in the box react to form the maximum possible amount of ammonia molecules, what is the limiting reactant and how many molecules of NH3 are formed? So let's write the reaction between H2 and N2 first and balance it in order to see where this goes. Remember, we can read reactions in terms of molecules or moles, and in this case, we are reading it in terms of molecules. So it looks like we have a 2 here and a 3 here, and the reaction is balanced. So for every 3 H2s and 1 N2, we will get 2 NH3s. So let's count how many H2s and N2s are in this diagram. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H2s. And how many N2s? Well, let's find out. 1, 2, 3, 4, 5. 5 N2s. Now the limiting reactant is the thing that produces less of the product. 12 H2s can produce, let's see if it's 3 to 2, then it's 12 to, it's going to be 2/3 of 12, or 8 NH3s. And 5 N2s can create twice as much NH3, so it would be 10 NH3. And it seems like our limiting reactant is our H2. So we will produce at most 8 molecules of NH3. So because of this, that's the maximum amount we can produce, and H2 is our limiting reactant. So it seems like C is our answer. So this is a review from the previous unit, and this is to see whether you are on guard. Next question. An adjustable volume container holds 10 grams of pentane. So let's draw a adjustable volume container, and it holds 10 grams of pentane with a molar mass of 72.15 and a normal boiling point of 36.1 degrees Celsius. The pressure in the container is measured as a function of volume while maintaining the temperature at 30 degrees. Which graph shows the results of this experiment? So if the temperature is under the boiling point, that means that not all the liquid will turn into gas, since if it was at the boiling point, then it would all turn to gas. So we know that the pentane is exerting some sort of vapor pressure, and in order to make that vapor pressure, the 10 grams of pentane has to evaporate, right? And it wants this vapor pressure, and we don't know what that is. But we can assume that at the very beginning, at a very low volume, the pentane will continue to evaporate in order to keep the vapor pressure of the pentane constant. So we know that at the beginning, the pressure will be constant, and there goes A and B for our answer choices. Now let's think about this. Let's think about whether, if we increase the volume enough, will there be enough pentane to make up that volume in order to keep the pressure constant? Well, let's try to figure that out. Let's see the maximum volume that 10 grams of pentane can fill up and still maintain the pressure at once. So according to C and D, it seems like the pressure is around 600, so we can assume that there are 600 millimeters of mercury worth of pressure, which is the vapor pressure of pentane that it wants. So here I changed the millimeters of mercury into ATMs, and I changed the grams of pentane into moles of pentane, and we know the temperature, which is 30 degrees Celsius. So I calculated using the vapor pressure of pentane that, it wants to have, and, I got the moles and I got the temperature, and I calculated that with 10 grams of pentane, you can fill up at most 4.38 liters and still maintain the pressure of 0.789, which is the vapor pressure of pentane. But once you kind of increase the volume to, if you increase the volume enough, then there won't be enough pentane to maintain the pressure that it wants. So it will start following a curve that looks like this. And this curve, you might notice, is when T and moles are constant, because our moles are constant since all the pentane evaporated, and if all the pentane evaporated, that means that, the moles of pentane in the air will be constant, and it won't be changing anymore, since none of it is liquid anymore. So if T and N are constant, and you compare P and V, it will form a little curve. And looking at our answer key, it seems like C fits our predictions, although this curve should be a little bit like that and not touching the x-axis. But that's our answer, so C is our answer. And I kind of explained this in one of the videos regarding vapor pressure, so go ahead and watch that. I talked about how if you run out of liquid, then you can't maintain a pressure, and all that good stuff. So let's move on to the next question. Number 12, a gas has a fixed quantity and volume in a closed container, so constant moles and constant volume. Which graph depicts pressure versus temperature? Well, let's think about this. PV equals nRT, and we have to move the variables to the left and the constants to the right. So P over T is equal to nR over V, and all this is constant. So we get that P over T is equal to K, or P equals KT. So pressure versus temperature is our graph, with pressure on the y-axis and T on the x-axis, like that. And notice how this P equals KT is the equation of a line that goes through the origin. So our answer will be A. And notice how it's not C, since this line doesn't go through the origin. The origin's right there, and it kind of goes below it. And this equation says that it goes through the origin, so that's why C is not correct. At STP, 2.00 liters of gas A2 and 8.00 liters of gas B react completely to form 2 liters of gas AXBY. What is the sum of X and Y? Now this is a very odd question, but we'll figure this out. So remember how at constant temperature and pressure, such as in STP conditions where the temperature and pressure are constant, we can read reactions in terms of liters. So let's write a reaction. A2 plus B becomes AXBY. And it says 2 liters of gas A2, so we can write 2 there, and 8 liters of gas B react completely to form 2 liters of AXBY. After writing this, you can read this reaction in terms of moles now. So let's read this in terms of moles. 2 moles of A2, or 4, I guess, atoms of A2, and 8 atoms of B react to form 2 times X atoms of A and 2 times Y atoms of B. So do you see where I'm going at? I'm going at the conservation of matter. So 2X A has to equal 4A, so X has to equal 2. And what about our B? 2YB is equal to 8B. So our Y has to be 4 because 2 times 4 equals 8. So 2 plus 4, which is X plus Y, is 6, and B is our answer. Alright, next question. At a constant temperature, 1.00 moles of radon and 1.00 moles of bromine gas have the same 1, 2, 3, 4. Do they have the same average kinetic energy? Well, yes. At a constant temperature, the average kinetic energy is always the same. Average velocity? Well, not exactly. Radon and bromine gas have different molar masses, and for that reason, at a constant temperature, they move at different speeds because one of them is bigger than the other, and according to Graham's law, bigger molecules tend to effuse more slowly. So therefore, 2 is wrong. Do they have the same density? Well, no. One gas is heavier than the other, and this is because at a constant state like STP, where temperature and pressure are constant, we know that 22.4 liters are in 1 mole. And remember how we calculated density in the first problem where we found the number of grams per mole? Well, if the grams per mole is higher, then the density will be higher because the density is the grams divided by the liters in 1 mole of substance. And as you can see, they're different for molar masses. So 3 is out. Effusion rate? Well, velocity and effusion rate are basically the same thing. This is just telling you how fast things flow through a pinhole, and this tells us how fast the molecules are moving. They're doing very similar things, and velocity and fusion rate are very closely related. So 4 is out, and our answer will be B, only 1. So let's look at our next question. So notice how I crossed out AT M's for ATM because I've gotten into the bad habit of writing ATMs when you're not supposed to include the S at all. You're just supposed to say like 5 ATMs, but when you write it, it's just 5 ATM. Like in other cases, for example, if I say 5 grams, I don't say 5 GS, I just say 5 grams. So I've been getting into a very bad habit of writing ATMs, and if you catch me doing that, then just ignore it, and remember to always use the unit ATM without the S. So let's read this question. 2.00 liters of gas has a pressure of 1.000 atms at 25 degrees Celsius. The closed container will shatter once the pressure exceeds 4.000 atms. What is the minimum temperature that the closed container will shatter? So I don't know if this is grammatically correct, but I think there's supposed to be an at there. So what is the minimum temperature that the closed container will shatter at? So that's grammatically correct, and now let's continue. So we have to look at what we're dealing with. So it's a closed container of gas, meaning that the gas won't escape, and that means the moles of gas is constant. And it seems that our volume is constant because it's a closed container, and it doesn't say anything about it changing volume. So let's assume those two cases, and let's do the question. So our volume and our pressure will change. So our relationship can be written at first as P1V1 over N1T1 is equal to P2V2 over N2T2. And since our volume and moles are constant, since this is a closed container, and there's no indication of whether the volume can change or not, then our V and N can be crossed out, and we get P1 over T1 equals P2 over T2. So let's plug numbers in. Our P1 is our first case, and our first case seems to be, well, let's see, 1.000 atms, and our first temperature is not 25.0, it's going to be 298.2, since we have to use kelvins at all times when we're dealing with gases. And this is a very important thing to remember. Now, it says it will shatter once the pressure exceeds 4.000. So we have to find the temperature at which it will reach this pressure, and at that pressure, it will explode or shatter. So what's the minimum temperature? Well, I don't know. Let's find out. So I've been doing this in my head, but there is a nice math trick for you to do. So you could switch the 1 and the t across from each other when you're dealing with equations, and you get, well, T2 over 298.2 is equal to 4.000 over 1.000. And notice how much easier the question gets. So it's 4 divided by 1 times 298.2. Notice how I'm doing algebra in my head. And I get a temperature of 1193 Kelvin. But our answers are in degrees Celsius. I know I didn't put the degree symbol, but you know that it's Celsius. So we have to go backwards. Turning Kelvin back into Celsius, we have to subtract 273.15. So 1193 minus 273.15. And we get that C is equal to, well, let's see, 920 degrees Celsius. And this is closest to 919. And it's probably just different due to rounding errors. And so the answer is B. Next question. A container contains 2.00 liters of nitrogen dioxide at 300 Kelvin and 1.23 atms. So notice how I messed up again and wrote atms with the S when you're not supposed to. If all the NO2 dimerizes pairs up into N2O4, how many moles of N2O4 will be in the container? So we have to think about this. Dimerization is when NO2 combines with itself to form, a pair, N2O4. And this is just because you just double everything. So using this reaction, let's figure out how many moles of N2O4 will, dimerize, since we're assuming all of it will dimerize, even though it won't in real life, but we're just assuming it. So if a container contains that many liters of NO2, we can write that as our volume, and our pressure is 1.23 atms, and this is equal to the moles of NO2. Remember, this is NO2 still, since we're looking at NO2 gas when we're doing PV equals nRT in this case, and 0.0821, and our T will be 300 Kelvin. So doing the math, we get 1.23 times 2 divided by 0.0821 divided by 300, and we get 0.0999 moles of NO2. And it says that all the NO2 will dimerize into N2O4. So for every 2 moles of NO2, we get half as many moles of N2O4. So we're going to divide this by 2 to get the moles of N2O4. So that divided by 2, and we get this as our answer. We will get 0.0499 moles of dinitrogen tetroxide. Alright, next question. Above is a graph showing the mole fractions in percent form of each gas in the Martian atmosphere. The Martian atmosphere is the atmosphere on Mars, by the way. At the surface of Mars, the air pressure is 610 pascals. What is the partial pressure of CO2 in pascals at the surface of Mars? So let's read this note that I wrote. You can keep pascals as your unit of pressure since we are not using PV equals nRT, which contains a constant that assumes P is in ATMs. And let's not include the S because I keep on doing that for some reason. However, always use K instead of C, and this is very important. If you decide to use C instead of K, you will get yourself into a lot of trouble in this chapter, so please use Kelvin instead of degrees Celsius. And when I say C, I imply that there's degrees Celsius there, but I just don't type it because I'm assuming that all of you know that there is a degree symbol before it, so I don't have to go through the trouble to do that. So this question is a mole fraction question. So the total pressure is 610 pascals. And you simply multiply by the mole fraction of carbon dioxide, which is 0.959. And multiplying these two together, you get 585 pascals for the partial pressure of carbon dioxide. So C will be your answer. A student collected 91.23 mLs of ammonia in a graduated cylinder above liquid ethanol. At 20 degrees Celsius, the vapor pressure of ethanol is 44.6 torr. If the measured pressure of the sample of gas is found to be 773 millimeters of mercury, find the moles of ammonia in the container. Now for this question, you need to know that the ammonia is being collected over some sort of liquid called ethanol, and ethanol has a vapor pressure. So this is a gas that contains both ammonia and the thing contaminating it, ethanol. So this is just like wet gases, except this time instead of water you have ethanol. So let's try to figure this out. What I would do is that I would try to find the partial pressure of NH3 and use the partial pressure to find the number of moles of NH3. So let's try doing that. We know that the total pressure is 773 millimeters of mercury, and the total pressure is equal to the pressure of the ammonia gas plus the vapor pressure due to the ethanol. So we have to subtract the total pressure minus the pressure caused by ethanol, which is 44.6. And notice how torr and millimeters of mercury are the same thing, so, you know, I just subtracted them since they mean the same thing. And that's a 6. And subtract 773 by 44.6, you get that there are 728 millimeters of mercury worth of ammonia gas. And converting this to ATMs, you get, well, let's see, you get 0.958 ATMs of ammonia gas in the container. So let's use PV equals nRT in order to figure out how many moles of ammonia gas there are. So our P is 0.958. Our V will be, well, the volume of the ethanol is just the volume of the gas. So 0.09123 liters. And this is equal to N, which is the moles, we don't know what that is, times 0.0821 times the temperature, which is 20.0 plus 273.15. And typing that into a calculator, we get 293.2. And when you do the math, we get that there are 0.00363 moles of ammonia gas in the container, so our answer will be A. Now let's move on to the next question. Which of the following is not a part of the kinetic molecular theory, or the KMT? So the KMT is describing a gas at an ideal viewpoint, I guess. And if you remember the KMT, you remember that it said that gases are mostly empty space. So A is out. The average velocity of a gas is the same at the same temperature. That's true. As long as the identity of the gas is the same. Collisions are elastic. Okay, that's true. And attractive forces make molecules stick. Well, I have a problem here because I remember that the kinetic molecular theory states that the attractive and repulsion forces don't really do anything, and they make molecules stick. I don't think that's what they're supposed to do. I think they're not supposed to make the molecule stick, so C is our answer. And if you weren't sure about this, you would read D. Gas pressure is caused by the collision of molecules with a container that contains the gas. That is correct, so you could have crossed out D, and you would have realized that C is the odd one out. Alright, let's look at number 20. Find the units for A in the real gas law, or the van der Waals equation. So we have 4 answer choices, and we have to choose the best one. So we have to calculate the units for this coefficient here, but how can we do that? Well, if you think about it, if you want to add 2 numbers together, like 5 plus 3, don't these two have to have the same unit so that when you add them together, they have only 1 unit for the answer? So if this was in ATMs, and this was in ATMs, then this answer should be in ATMs. And note how the 2 numbers that you combine together have the same units. It goes the same for adding lengths. If you want to add 5 inches to 3 inches, you will get 8 inches. It doesn't make sense for you to add 5 inches and 3 feet to get 8 inches because they are in different units. So when adding 2 numbers, you unconsciously figure out that the units for both of these numbers should be the same, or else you can't add them. So if pressure is being added to AN squared over V squared, then these two should be in the same units. So if P is in ATMs, and what would AN squared over V squared be? Well, this would also have to equal ATMs, because if you add these two together, you get a pressure in ATMs. And let me just erase that S. So we have to make sure that this altogether means ATMs, so that when you add this and this, you get an answer that's in ATMs, which was the intention of the question. So let's try to figure out what the units are for A. So A times N squared. N is always in moles, so use moles squared. And volume is in liters, so liters squared is equal to ATMs. Now, if you multiply both sides by liter square over mole square, you noticed that the mole squares and liter squares cancel out, and you were left with A. So A is equal to ATM times liter squared over mole squared. And notice how the answer looks just like C, which states that ATM times liter squared over mole squared is the units for A. So C is our answer, and that's all for this video. Thank you for watching, and have a nice day.